Hello, calculus. We're going to talk about physics today. We're going to talk in particular about two-dimensional motion. And I'm going to kind of run through a bunch of stuff that you already know and then tell you a couple things that you don't know, or maybe you suspect, or I don't know. Anyway, I'm going to tell you about them. So two-dimensional motion, what does this have to do with parametric equations, which we've been talking about for the past couple days? So if x of t and y of t are parametric equations, are the horizontal position and the vertical position of some object, then we're talking about parametric equations, but we're talking about physics and two-dimensional motion. So we've done this. This is really not anything new. In fact, we've been doing this since really chapter 4 in physics a long time ago. And we know about if you take the derivative, then that's the horizontal velocity, and if you take, there's different ways you can write that, I'll write them all here, dx dt, and then if you do y prime, that's the vertical velocity, or dy dt, and if you take the derivative again, that gives you the horizontal component of the acceleration. And likewise. So in other words, you know, all the calculus stuff that we already know is still a thing. Now, what if you wanted to know, all of these things are vectors. And when I say all, I mean position, velocity, and acceleration are vectors with a magnitude and a direction. And you know how to find the magnitude. You do the Pythagorean theorem on the components, whichever one of them you have, and the direction, you do tangent inverse rise over run and figure out what quadrant you're in and all that kind of stuff. We know that's just basic geometry stuff, and we've done it in physics already. So nothing really special to say there. If you want to know, it's common, it's actually very common, you'll start to realize, especially when we get into free response questions of this type, very common for you to be given the components of the velocity, the horizontal and vertical velocity, as functions of time, either dx dt, dy dt, or sometimes they write them like that, the College Board. And then you have to do other stuff from there. So, of course, remember the fundamental theorem. If you have the horizontal position and you want to get back to, the horizontal velocity and you want to get back to position, that's a fundamental theorem problem. Take the antiderivative, don't forget to use your initial condition and all that. So that's nothing new there. What else? Well, in one dimension, total distance traveled is equal to, do you remember? Pause the video and just think for a sec. Total distance traveled is the integral of the speed. And in one dimension, that speed is 1d speed is just equal to the absolute value of velocity. Because the only thing that's going on direction-wise, if you're in one dimension, is it's either positive or negative. So your speed is just, well, ditch the negative sign and keep the positive version of it. Now in two dimensions, do you know what total distance is? Total distance is equal to the integral of speed. Which is convenient. So it's the same thing. It's the integral of speed dt. But the difference is in two dimensions, speed is the, if you think about the components of the velocity, the x component and the y component, the speed is the hypotenuse of that. 2D speed my poor Sharpie is dying here. 2D speed is equal to the integral from some time to another time of, oh, whoops. I just wanted to say here 2D speed is equal to, so I don't want this part, sorry. I'm actually rewriting the expression for total distance there, which is not what I meant to do. So 2D speed is just the Pythagorized components of the velocity. Like that. Good? That's how you find total distance. Let's see, what else would we want to do? So your average speed would just be why did I write a D there? That's weird. 2D average speed is, you know how to find the average value of something? The average value of speed would be the total distance divided by time, right? So that would be this integral divided by the time interval. And let's see. If you're asked, this is not something that comes up too often, but if you're asked about speeding up or slowing down, you cannot do the same game that we did in one dimension, where you think about the sign of the velocity and the sign of the acceleration, and if they're like fighting against each other, it's slowing down, and if they agree with each other, it's speeding up. That doesn't work in two dimensions, because what if in one dimension you have like positive for your velocity and acceleration, and the other dimension they disagree with each other? Then you kind of need to, like, which one's more? So that's not really the way to go at that. So speeding up or slowing down, we want the sign of the derivative of speed with respect to time. Now that would be d this dt, right? And this should not dt does not belong. Sorry, can you see where I am at there on the sheet? From the days when I was writing this integral there and wishing that I had a dt there, or maybe it's just in my brain I was going to write a dt there. So two-dimensional speed is just this, right? Not with a dt there. So if you had that there, please get rid of it. Okay, so how do you find if it's speeding up or slowing down? You look at the sign of d speed dt. If you're thinking to yourself, oh my goodness, that is going to be a nasty derivative to find there, these are going to be with calculator problems. So you just have to enter. My advice to you would be, when you are given the dx dt and the dy dt, put those in as y1 and y2 in your calculator, and then do everything from there. You'll see me do examples in the solution videos for the free response questions, how I handle that. All right, I think one more thing I need to tell you about the motion problems. So if this is the speed right here, then what is dy dx? That's one of the things we learned to do in our little parametric exercises, right? You dy dt over dx dt. What's that? Is that not the speed? No, it's not the speed. Notice that there's no t in there. Of course, when you do it, it's going to be an expression with t's in it, but it's telling you what dy dx is. And so what's that? That is the slope of the actual path that the particle is traveling on. Very common mistake, try not to make it, is to be asked to find speed and then to do this instead. Right? This is not, you don't do dy dt over dx dt to find speed. That finds the slope of the path. So if you wanted to find the tangent line to the path, then this is how you find that slope. You would need the point, and then this is how you'd find the slope. All right. One more quick observation here is that if total distance, I'm just going to write this again, if total distance is equal to the integral of speed then if we remove this from the context of, if this is just like some parametric equations and it's not necessarily describing motion, or we're not thinking about it in this way, then we could understand this expression to be the length of a curve in the xy plane. And that's something we've never done before. We never knew how to find the length of a curve. And it makes sense. Total distance traveled, yeah, that's the length of the curve. It's just that this works also to find lengths of curves when we're not necessarily thinking about it as a motion problem. So length of a parametric curve is equal to this, same expression. And then by doing a very, very basic substitution, what about like a y equals x function? Like what if we wanted to find the length of a regular curve, like not a parametric curve? It's really easy to get to from this. To get back to good old y equals f of x, not parametric, you just let x equal t and y equal f of t, right? In other words, you can turn y equals f of x into a parametric equation really easily and then go back the other way. So if that's true, then that means from this equation here, dx is equal to dt, right? Because those two things are equal to each other. So substituting here, everywhere where I see a dt rather, I'm going to substitute dx. So what's dx over dx? That's just 1. Squared is just 1. Plus dy dx squared dx. And then these would be x values instead. So the length of function y equals f of x is equal to the integral x1 to x2, the square root of 1 plus dy dx squared. So that comes straight from this. And in the multiple choice problems that I'm going to ask you to try, there's a few of these. It's pretty tricky to craft a problem where this turns into an integral that you can actually do by hand. So it's pretty common for these to be calculator problems when you want to find the length of a curve. All right, that's what I got for you for notes for 2D motion.